Okay. uh, Today actually I'll show you some numerical problems. Okay, which are actually you have solved in your soil mechanics, but when you have solved, you had no idea about the compaction, or you had no idea about the things which are involved in the numerical problem. So today's class, I will take very the less duration class, and this during this class just I will show you uh, two numericals, okay, regarding your compaction chapter. And after that, from the next class we will start the stability of stability of slope. Okay, the core chapters of foundation engineering. Basically, in earlier syllabus, uh, your seniors, those they have studied this compaction consolidation in their soil mechanics portions. Already they have completed in this portion in soil mechanics, but from you and I think onwards, now the compaction and consolidation will these two chapters will be studied in the soil mechanics 2 or foundation chapter. But the compaction and consolidation both are very much related to your soil mechanics, and further chapters like the Amisar is giving you the or Amisar is teaching you the chapters like your shallow foundation, this shallow foundation, stability of slope, earth pressure. These are the core chapters of foundation engineering. Okay, so just I will show you today I will show you the problems which are related to compaction. Even these problems are very important because for gate exam as well as your any civil service exams or competitive exams. So in soil mechanics, these are the some the special type of questions or the questions in Purnia book, BC Purnia book. It is mentioned that examples from competitive examinations. So my suggestions is all of you please try the problems which are given in examples from competitive examinations in BC Purnia book. If you have at that at this situation, I think maximum you don't have the basic Mumia book, but when it will be available to you, you should go through the examples from competitive examinations which are given in BC Mumia book. Okay, so such type of one problem I have taken, which is given in your preliminary definition and relationships chapters. Like from the very initial chapter, I have taken this question, but this question is related to compaction. When we normally, even in my case, when I was in BTech or BE, when I was solved this problem, first I have when I had solved this problem, I had no idea about the compaction. Okay, but after compaction, after completing the compaction chapter, this problem is very easy to all the students of soil mechanics or in of civil engineering sections. So now let's start the question. The question is a core cutter. Achha, the problem is all of us for us this core cutter is not the very common thing or very known thing from the beginning, but when compaction chapter is over, now this core cutter is very known to us. All of us have some idea about the core cutter. So a core cutter 12.6 centimeter in height and 10.2 centimeter in diameter, weighs 1071 gram when empty. Now these things are clear because we know this is some dimensions are there in core cutter, and some weights are there in core cutter. It is used to determine in situ unit weight of an embankment. It is used to determine in situ unit weight. Okay, in situ unit weight of an embankment. Embankment is the deposition of soil. Okay, the weight of core cutter full of soil is 2970 gram. If the water content is 6%, what are the in situ dry weight and porosity? If the water content is 6%, what are the in situ dry weight and porosity? This is the first, I think this is the first question. And number 2, if the embankment gets fully saturated due to heavy rains, what will be the increase in water content and bulk unit weight if no volume change occurs? And the specific gravity of the soil solid is 2.69. This question is taken from the civil service exam 1997. Now let's go to the solution. First, calculate the volume of the core cutter. Okay, calculate the volume of the core cutter. Very easy. Pi by 4 d square h. This formula should be used for your future also. You should use this formula to calculate the volume. Pi by 4 or pi d square by 4 into h to calculate the volume, and to calculate the area pi d square by 4. Pi d square by 4 is the common equation to calculate the area and easy to remember. And to calculate the volume, I am actually why I am talking about this, because some of us normally we are followed the conventional equation in our which we have taught in our school. So regarding, suppose in school we have studied the area. Area is the pi r square normally. Okay, pi r square. We have studied pi r square, but my suggestion is, if you remember this formula pi by 4 d square, this will be easy to remember. Or normally this formula is basically used when we calculate the area. So normally we have required the volume V equals to pi by 4 d square h. This is the volume. Mass of soil sample already given 2970 gram. This weight actually mass of weight of core cutter plus weight of soil. So and weight of the core cutter is 1071, or empty weight of the core cutter 1071. So mass of soil is 2970 minus 1071, 1899 centimeter cube. Therefore density is mass by volume. This is the mass and this is the volume. So density is 1.844 gram per centimeter cube. Acha, when we talk about the density, the unit should be gram per centimeter cube, and when we talk about the unit weight, the unit would be kilonewton per meter cube. Okay, so you can see here this density has been converted to the unit weight. Okay, 1.844 into 9.81, that's why 18.094 kilometer per meter cube. Normally in practice we can multiply with 10, no problem. If you multiply with 10 as a civil engineer in any exam, it is okay. But maybe in gate exam it may problem, it might be problem, but normally you can multiply with 10. Okay, you can multiply density with 10 to get the unit weight, and this unit is very important. Okay, when density gram per centimeter cube, when unit weight kilonewton per meter cube. Now next is the dry density, calculation of dry density. Same formula, bulk density rho by 1 plus W, 1 plus water content. So bulk density is 1.844 by 1 plus 0. Water content was 6%, that's why. Acha, remember this 6% means 6 by 100, and this water content should be 6 by 100. That's why 0.06. Now the dry density of the soil is 1.74 gram per centimeter cube, and the unit weight of the sample is 1.74 into 9.81, 17.707 kilometer per meter cube. These things are common, or these things are now you can understand, because compaction chapter is over. So these things are well known to you. Next is this is the portion which already covered in your soil mechanics part, or the first chapter of soil mechanics, that is the preliminary definition. In preliminary definition part already you have seen such type of formula. Okay, E equals to G gamma W by gamma D minus 1. This formula you have seen in your initial chapters of soil mechanics. G is the specific gravity 2.69, already mentioned in question. Gamma W is gamma W. What is gamma W? Gamma W is the unit weight of water. Another thing, unit weight of water. When unit weight of water in kilonewton per meter cube, then you should take 9.81 or 10. Okay, but when unit weight or density, density of you have to take density. Suppose unit is gram per centimeter cube, then the density of the water would be 1. Okay, when your unit is kilometer per meter cube, the unit weight of the water would be 10, and when your unit is gram per centimeter cube, the density of water would be 1. And in fluid mechanics you have seen, when your unit is kg per meter cube, okay, kg per meter cube, then you have to take 1000 kg per meter cube, the unit weight or density whatever of water, 1000. Okay, these things should be clear, because maybe in question it might be mentioned that the water content should be taken in MKS unit, water content should be taken in SI unit, or water content should be taken is, or the unit should be taken as, or unit may be given as in your SI unit or MKS unit or your CGS unit. Okay, now the void ratio is available from this formula. And we have got this, what are the in situ dye density and porosity. Okay, next is number 2. If the embankment gets fully saturated due to heavy rains, what will be the increase in water content and bulk unit weight if no volume change occurs? When the embankment gets saturated, E remain the same, since water outer by expelling air from the voids. Now E equals to W saturated into G. W sat equals to E by G. These formulas are coming your soil mechanics part, or the initial chapters of soil mechanics. So E equals to 0.546 by G is the specific gravity 2.69. Now W sat equals to 20.3%. So increase in water content 0.203. This is 20.3 by 100, that is 0.203 minus 0.6. 0.6 is your actual in the water content is 6%. In situ density. If the water content, this is actually bulk water content, and this is the saturated water content. This is 0.203 or 20.3%. So the increase in water content is 14.3%. Also, gamma saturated unit weight equals to gamma D. This is the formula, gamma D into 1 plus W sat, that is 17.07 into 1 plus 203, that is the saturated unit weight of soil. Increase in bulk unit weight, therefore this is the saturated unit weight, and this 18.094 we have this value soil sample, uh, this value, okay, actually this value 18.094 kilometer per meter cube. This was our bulk unit weight, and this is our saturated unit weight. So increase in bulk unit weight is 2.441 kilometer per meter cube. These formulas are available in your soil mechanics part. The initial chapters, these formulas already are given, and you can find out, or you have studied this kind of formulas in your soil mechanics part. Same type of problem. Next problem is regarding your compaction chapter. So soil is to be excavated from a borrow pit which has a density of 1.75 gram per cc. Soil is to be excavated from a borrow pit. Okay, borrow pit. What is borrow pit? Borrow pit is the big hole. Okay, big duct in the earth surface. The soil is to be excavated from a borrow pit which has a density of 1.75 gram per cc and water content of 12%. The specific gravity of the soil particle is 2.7. The soil is compacted so that water content is 18% and dry density is 1.65 gram per cc. For 1000 cubic meter of soil in field, estimate number 1, the quantity of soil to be excavated from the pit in cubic meter, and the amount of water to be added also determine the void ratio of the soil in borrow pit and fill. Let's see the solution. Solution is the given unit weight of the soil is given of the borrow pit. Water content is given. These are the natural or bulk. Okay, this is the bulk water content. This is the bulk unit weight. Natural, which is all the values which are given in or which are taken from natural conditions. Suppose now somewhere the rain is going on. Okay, if we take the soil from this open environment when rain is going, or suppose throughout the night the rain has going on, or the rain has there, at that situation if we collect, suppose in the morning time we are collecting soil, this is called the bulk condition. Even in dry season, suppose very humidity is very less, no humidity is there, very dry condition, and we are collecting soil, this is called also the bulk condition. Okay, natural condition without influencing any kind of artificial things. When we collect the soil from the environment, that is called the bulk condition, natural condition. The bulk is the standard word, so bulk condition. So these are that bulk conditions of soil. Okay, this is a bulk unit weight, bulk water content, and specific gravity also given in the question 2.7. After compaction, the dry unit weight of the soil is 1.65 gram per centimeter cube. These questions already were given in your initial chapters, but now after completion of your compaction chapter, now these things are become very easy to you, because now you can understand what is gamma d, actual gamma d, where we can find out the gamma d. Now what is the relation between this dry density, water content, okay, bulk density. Now these things are easy to you, understandable. So after compaction, gamma d is 1.65 gram per centimeter cube, water content is 18%. Let us use suffix 1 for borrow pit and 2 for fill. Okay, for borrow pit, this is the density. The borrow pit density is this is the formula, because we have specific gravity, water content, the density of water, and water content, and the void ratio. So now we can calculate the void ratio. Okay, and let us use suffix 1 for Borofit. So void ratio of Borofit, E1 is this formula, G rho W into 1 plus W by rho minus 1. Now after calculation, the void ratio of the Borofit is 0.728. Okay. Now for the fill, the question is said that the soil is compacted, so the water content is 8%. For 1000 cubic meter of soil in fill, estimate. So 1000 cubic meter of soil is available to fill the Borofit, and for the filling, for the filling we are calculating the E value of the soil, E2, because for Borofit and 2 for the fill. For the fill, 2 will be used as a suffix. So E2 is the void ratio of the filling soil. The formula is rho D equals to G rho W by 1 plus E. That is the dry density of soil. Dry density of soil is equals to G rho W by 1 plus E. And we can calculate the void ratio value of soil, filling soil. Now the value is 0.6364. Okay, since the volume of solids remains constant. Okay, volume of solids remains constant. So Vs equals to V1 by 1 plus E1 equals to V2 by 1 plus E2. Okay, V2, what is V1, V2? V1 is this 1000 cubic meter. Okay, the filling soil 1000 cubic meter, and E1 plus E2 should be the same, or we are taking this value should be equal to this value, and if we put the value of V2, that is 1000, value of E2 is 0.6364. Now the Vs would be 611 or 611.1 meter cube. Okay, and V1 is the 1056 meter cube. In general, W equals to MW by MD, but MD equals to MS, mass of solids, equals to Vs into G rho W. Now MW1, that is MD into W1, 1649.97 into 0.12. 0.12 is the water content, and this value is 197.996 meter cube. MW is 296.995 meter cube. Water to be added, MW2 minus MW1. This water should be added for the complete fill up the Borofit. Okay, that this is a water content actually. W is MW by MD, weight of water to the dry weight of soil, and MD is the actually weight of soil, mass of solids or weight of soil, dry soil. Vs, and this formula is Vs into G into rho W. We are getting this 1649.97. MW1 is MD into W1. MD is 1649.97 into this W1. W1 is 0.12. Okay, this W1 water content, this W1, and MW2 is 1649.97 into 0.18. This water content, compacted water content. The water to be added 99 meter cube. Okay, this type of problem can be solved, or these problems are related to your compaction, or you can or you might be faced this type of problem in your exams as well as in your competitive exams, where compaction is involved. Another thing I am showing is this is your syllabus of your soil mechanics 2. Okay, in soil mechanics 2 already we have completed this consolidation part, consolidation of soil, compaction of soil. Okay, already we have completed this these two chapters. So already we have completed, and the Amit sir, I think Amit sir is started this bearing capacity of shallow foundation, and after that I will go to the stability of slopes, this chapter. Okay, stability of slopes, this is the core chapter of the foundation engineering. Normally foundation engineering is the common term, um, but then in new syllabus the soil the syllabus authority has specified by two names, that is soil mechanics 1, soil mechanics 2. In soil mechanics already in earlier syllabus, these compaction and consolidations, both these chapters are included in soil mechanics part, but now you are you are getting this compaction and consolidation in soil mechanics 2 part, whatever. But this earth pressure, this bearing capacity of shallow foundation, settlement and stability of slopes, these are the core chapters of foundation engineering. Okay, even you if you enroll in NPTEL, the foundation or the geotechnical part 2, also you can see in NPTEL syllabus also these chapters are mentioned. This earth pressure, bearing capacity of shallow foundation, settlement and stability of slopes. So from the next day I will start this stability of slopes. Okay, uh, for stability of slopes, for the better understanding the stability of slopes chapter, you should keep your all the geometric instruments. Okay, I think drawing instruments most probably, uh, like compass, protractor, scale, pencil, eraser. Okay, these things should be ready with you, and most probably some graphs are required to draw some things. Okay, from the next day you should be ready with the scale, pencil, eraser, compass, protractor, and maybe graph paper is required. Let's see, no problem if you have not graph paper. Okay, but you should have the compass, protractor, pencil, eraser, scale, and if you require sharpener, you can keep you with you. Uh, for stability of slopes, normally in semester chapters, uh, graph is not common. In semester graph is not common, but for better understanding, you can you can practice with graph paper. Okay, because analytical equations, analytically we can calculate the stability, as well as graphically also we can calculate the stability of slopes. The first thing is what is slopes. I will give you next day. But stability of slopes, one of the important part, and all the landsliding. Okay, landslides normally in hilly areas. Now the rainy season is going on, so lots of landslides are going on. Lots of landslides are taking place in the hilly region or hill stations. Okay, so this is one of the challenging part of civil engineers. Okay, this part is also challenging. Okay, I am taking attendance. Just wait. Wait.